Hello everyone, welcome to this video. My name is Arid. I am a Google Earth Engine expert. In this tutorial, I'm gonna show you how to calculate urban heat island for an urban area in the arid and semi-arid region. If you follow my YouTube channel, in the previous video, you saw that how we can do urban heat island detection for the urban areas surrounded by vegetation cover. So in this tutorial, I'm gonna do the same with another satellite data, MODIS land surface temperature product for arid and semi-arid region. So now in the first step, I'm gonna select the study area. Through the search places and dataset, you will be able to find FAO administrative borders for the all provinces in all around the world. So here type FAO administrative. As you can see, in different levels administrative units available. The first level correspond to the province borders, so imported into the code as a table. Through the mapped add layer, you will see that how it covers global. So as you can see, different provinces in different countries covered by the FAO administrative layer. So in this tutorial, I'm gonna have focus for urban heat island in the arid and semi-arid detection in the semi-arid region. So that's why I'm gonna to select Tehran, the capital of Iran, as a region that is including actually this province, including Tehran, a big city in the Iran, the capital of Iran, that's helping us to do the urban heat island detection in the arid and semi-arid region. As you can see, Tehran is a kind of city that is not surrounded by vegetation cover such as northern region. So you can use this tutorial for all of the urban areas, at least for the big urban areas in the arid and semi-arid regions in all around the world. But in this tutorial, I'm selecting Tehran as a region of interest because I know this region, and also this tutorial can give you good insights about urban heat island in such kind of region. So through the geometry tools available here, through a marker, I'm selecting the region including the Tehran, the province including the city I want to do urban heat island detection for. So in the next step through the code, I can make a clip based on the marker. So it's very simple. Make a new variable. Here the new variable is a region of interest equals to, from the table dot filter bound, we can filter the layer based on the marker that is geometry according to the location of the marker and filter bounds. So now I'm trying to have focus on the study area through the map.center object ROI, and then I'm gonna visualize it through the map.add layer. Save the code and run it again. After a few seconds, you have focus on the target area, and also you can see only the region of interest that you selected through the geometry. In the next step, we need to call land surface temperature data from MODIS satellite products available in the Google Earth Engine platform. A new variable MODIS equals to, through the search places and dataset, just type MODIS temperature product. Various MODIS temperature products available, some of them related to the, for example, Aqua, some of them related to the Terra. Here you can see the land surface MODIS temperature. Let's write it again. MODIS temperature. Yes, as you can see here, some of them related to the Terra satellite and another one related to the Aqua satellite, but all of them are providing land surface temperature and emissivity with daily temporal resolution and 8 days product. For the urban heat island detection, it would be better to use multi-temporal data such as 8 days products because they contained less cloud cover and less noises and provided higher quality images for such kind of analysis, because high frequency and interval is not matter in the urban heat island detection, and most of the time we need an average image from a single season or a single period of time over a year or anything like this. And also we don't need to do high frequency data analysis or high temporal resolution such as the daily or such as daily actually. So now I'm gonna import 1 kilometer data with 8 days temporal resolution from Terra satellite. So import it into the code, and as you can see, the data has 1 kilometer spatial resolution, meaning that it is one of the coarsest spatial resolution satellite data, and you can use this product or this kind of data for the big cities. For the small cities, maybe you don't get very appropriate result in this regard. That's very important to use this product for the big cities and metropolitan area such as Tehran. So MODIS equals to image collection. Assign the image collection to the MODIS. As this is a coarse spatial resolution data, no need to set the filter bounds because it doesn't have framing structure such as Landsat images. The only thing is matter is the temporal the temporal extent. Through the dot filter date, you can set a starting date and ending date. I'm making a new variable, time start, two new variable, one of them time start and another one is time end. And here time start before variable, insert the time start any year or any specific year you are working. For example, I'm gonna to plot the urban heat island changes in my study area for 2020, for example. And also the time end could be, for example, 2021, as I have used VAR before time start, and after comma no need to repeat VAR again. So as you can see, for 2020 I'm gonna call all the MODIS data available, and if you go to the MODIS data description, you can have access to a short description about data characteristic, and the citation will help you to cite the data in your paper. And also in the bands, you can see the different bands available for the land surface temperature. One of them is LST nighttime land surface temperature, and another one is the daytime land surface temperature. Actually, for the arid and semi-arid region, it's important to use nighttime data because in the nighttime, the urban area mostly has actually higher temperature compared to the surrounded region in the arid region and semi-arid region. But in the case that no vegetation cover available around the city, because if your area is surrounded by the vegetation cover, in the night time definitely you will see high temperature around the city. That's because of the vegetation cover. So, and now I'm gonna use land surface temperature night with 1 kilometer spatial resolution as a target band here, and we have one scale factor that should be applied on the data, but it is not actually necessarily to do, but you can do it. It is optional and completely up to you because LST already calculated in this product, and also the scale factor is only a coefficient that helping us to range the values from the integer to Kelvin range. That's it. So, and here through dot select, I'm selecting the target band that is LST night with 1 kilometer spatial resolution. So now through the print you can see or check how many MODIS images available for this period of time. For 1 year, 46 image available for each date, and also for each feature one band selected that is equals to LST nighttime data. And now in the next step I can make an average image from the LST data, LST night data, that gives you a more insight about the nighttime LST data characteristic. So through the map.add layer, I'm gonna use MODIS data, the all LST night data provided for 1 year, and then I'm gonna make a median image from all of the data for 1 year, and then clip it based on the region of the interest, and then I leave the visualization parameters empty. The layer name setting should be for example MODIS LST night, and use the false at the end to avoid automatic visualization. So now a new layer created in the layers, it is MODIS LST night, and also you can increase the speed of processing by simplification, by doing some sort of simplification in the border of the region. Actually, it's very simple and easy to use technique. For example, through the map, I can make a new function to apply the simplification technique. The function input is a feature, each input feature here entitled as f. I'm returning the input feature with a simplify function. For example, I set 1000 as a scale that apply as a scale applying simplification degree on the existing layer actually. And now it's a little and also the simplification help us to see the final result easier, and also it highly reduces the number of extra vertices available existing in the border of the region, borders in the region of the interest. So I'm stretching the LST night data, and as you can see, this is the LST night data that showing the urban area here with the higher brightness value, that you can see that this region correspond to the urban area in Tehran. And using the transparency tools available here, you can see that in the urban area we have higher temperature. That is very helpful in the arid and semi-arid region to detect the urban heat island with more accuracy. So back to the processing step. After you get some basic information about LST data, then I'm gonna set a filter to span this data or limit our data to a single season, for example to a winter, because in the winter the temperature is lower, and also we expected a better contrast between the temperature of the urban area and temperature of the non-urban pixels. So it's very simple. We can add a new filter as calendar range, Earth Engine.filter.calendar range, helping us to select a specific month, a specific day, or a specific period for our data during the process. For example, the field of study here, the target field is the months, and according to the months, I'm gonna only call the MODIS LST night from January to, for example, March, from the month number 1 to the month number 3. So now I'm running the code again. A new LST is ready now, and through the stretching techniques available here, improving the spatial, improving the contrast, and you can see we have a little better contrast to detect the urban area as a hotspot here compared to the other compared to the other regions. So imagine that now for this time I'm gonna make urban heat island map for the region of interest according to the equation and the method that I have already introduced in the first part of this tutorial that is already published in my YouTube channel. So to calculate the urban heat island index, first of all, we need to get an average temperature for the region of interest. The average temperature for my region can be calculated through a reduced region function. Make a new variable. So here I'm gonna get the temperature average, temperature mean equals to get all MODIS data for the winter time, and then through the reduce region I will be able to get the average temperature for the whole of region. So the reducer is a kind of function helping us to call statistical operations such as mean, minimum, maximum, and standard deviation or something like that. Earth engine reducer mean, I'm getting average here. If you want to get the maximum, just type the max instead, and also do it for the other statistical operations. Next is the region of the interest or the geometry. The region of interest is ROI, and after this scale for the processing should be 1000. Temperature data in the MODIS sensor has 1 kilometer spatial resolution and scale should be 1000 meter. So to get the final value as a value or number, use that values because it has the reduced region provided the output with dictionary format. But if you want to convert it from dictionary structure to the number format and number structure, you must use that values and .get helping us to get the first item in the dictionary. And if you want to convert it to a number, if you want to show Earth engine number, ensures that the output will have number format. That is very important. Through the print, I can get temperature average for the region of interest, but if I want to but before this I need to change the MODIS actually to add median filter here. Add the median function at the end of MODIS variable to get the median or average value for the winter time. But the question raised here it is why we are using median instead of the average. Remember that one benefit or advantage of median compared to the average in the satellite image processing is that average always including the impacts of the minimum and maximum values or outliers. Extreme minimums and extreme maximums highly will have impact on the final estimations or the final maps, but median get a better insight and perspective about the region of the interest and less affected from extreme and outlier values that coming from, for example, dust or cloudy sky or the sensor noises. So no need to have that median here anymore in the map.add layer, and also we can change the MODIS name to the winter because I'm using this actually this code for the winter time, and then I'm clipping the winter image based on the region of interest, and here I'm getting winter average using input data for winter time, and then we can have winter average for the region of interest. if you run the code, a new number is calculating. This is the average temperature value, but this is not a real temperature. As I mentioned earlier, if you want to have a real temperature data in the numbers for interpretation, you need to apply the scale factor value that is 0.02, that returning actually the Kelvin unit for the measurements. Now using the scale factor, the data transformed from the original range to the Kelvin range. It means that the average temperature for this selected period of time in winter time, it is 270 Kelvin. So in the next part, I'm gonna use the average and winter time image to get the urban heat island index. So just make a new variable. This is the winter urban heat island equals to get winter image first, and then through the expression write the desired or target equation. My target equation has two parts. The first part is a subtraction between the input image or winter image and the average, and the second part is a division to the average image, to average value or average temperature again. So winter and mean both are unknown variables, and now I can define a known and also calculated variables for each here. The first is the winter should be equals to the winter layer, and the next is average or mean should be equals to winter mean. So the output will be an image because the winter has image structure, and we can set a new name for the output that is UHI. So now in the next part, I'm gonna visualize through the map.app layer. I'm gonna visualize the winter urban heat island image that is clip based on the region of the interest or ROI, and I leave the visualization parameters empty, and the layer name could be same winter urban heat island, and use the false at the end. Run the code, and after a few moments we have winter urban heat island image that visually it has no such difference with compared to the previous image or the original LST that I have showed you. But the only thing changed here is the range of value. To know better about the range of value, so here you can use the histogram structure, user interface .chart.image.histogram, helping us to get insight about the range of value in the winter urban heat island product. The target image is winter urban heat island, and then the region of interest ROI, and the spatial resolution is 1000 meter. In the right panel under console, you can see the regions or the distribution and frequency of different values in the image. We only need to work with the positive values in this image, because the positive values helping us to find the urban heat islands or heat islands, or those of regions that have higher temperature compared to the average. So, and in the next step we will get rid of actually the negative values in the further processing, and it is anticipated that in this index the urban area has higher temperature, and also this is a part that helping us to detect the urban heat island easily. Although maybe the other regions, in the arid and semi-arid regions, it is common you have some sort of actually heat islands out of the urban areas. It is common and typical, but to remove these noises, because we only want to have focus on the urban area, to actually solve this challenge, finally we can mask our image based on the region of the urbans, or we can mask the image according to the urban class it is available in the land cover maps, and I will show you how to do it. So now I'm gonna actually show the winter urban heat island again, do the visualization and throw the inspector. If you click on the urban area, you will see that it is including the positive value. Each range of value in the winter urban heat island image has a specific meaning. So there is a reference for this index published in Environmental Challenges, and you can find it in the Science Direct. This is the title of this paper in the Science Direct website. Actually, the index I'm using here introduced as UTFVI, Urban Temperature Field Variance Index, that is a subtraction between surface temperature and a subtraction between surface temperature and average, divided to the average temperature for the region of interest. And for the UTFVI, there is a manual classification that mentioned in the table here. Yes, here we have a threshold values for UTFI. That this kind of classification definitely help you to understand the intensity of thermal variance or temperature variance over the urban areas, and also to separate the urban region from the surrounding region to visualize the urban heat island easier. So as you can see, we have different classes about the weak, middle, strong, stronger, and strongest. And now I'm gonna show you how to use this kind of manual thresholding technique to classify the urban heat island image or winter UHI in the code to get better insight for the interpretation of the result. So make a new variable, urban heat island, and also the variable name is urban heat island class equals to first we need to make a constant image. Earth engine dot image dot constant is a actually constant image that we are going to fill it according to different conditions, different conditions and different classes and different range of values existing in the winter UHI variable. So now the first condition, back to the paper, the first condition, we don't need to the non-class, we leave them empty, but the first class is the weak. Values ranges from 0 to this value related to the weak thermal variance in the region of interest. So to write this condition, we can use where as applicable function here, that where helping us to set to replace a range of values with a class label or the class number. For example, that where in the pixels in the image constant in which the winter UHI values are greater equal than 0, and those of pixels in which winter UHI values dot less than, as you can see, between 0 and this value, and less than 0.005, like this, label them as number 1 or class number 1. Here I'm setting a label, a number label to the pixels starting from 0 to this value. So the next condition, that where again in the winter UHI image those of pixels greater than equal the last maximum value dot and those of pixels in which urban heat island values are less than the next threshold is 0.01. Copy and paste it like this. Label them as number 2 or class number 2. So again, for the next condition, those pixels in winter urban heat island that are greater than this value and those of pixels in winter urban heat island dot LT are less than 0.015, label them as number 3. Again, that where we can repeat this process for all the conditions that where winter urban heat island greater equal 0.015 and those of pixels are less than 0.020, label them as class number 4. And for the last one, if you check in the description, the pixels greater than 0.020, label them as the strongest class. So here pixels in urban heat island that are greater equal than 0.020 label them as class number 5. The first class is weak. In the first class and also we can say that in the new image those of pixels labeled with 1 showing the weak thermal variance, and also those of classes or those of pixels labeled as 2 showing a middle thermal variance, and class number 3 showing strong, as you can see in the description, actually showing the strong thermal variance, stronger and strongest, like this. Class number 4 labeled as stronger, and class number 5 is the strongest, that we expect to see class number 5 in the urban region, at least in the winter time and also in the nighttime data for the land surface temperature. So now through the map.add layer, visualize the urban heat island class. So clip it based on the region of interest, ROI, leave the visualization empty, and the name is UHI class, and then use the false at the end. So as the output or for urban heat island class is classified based on different threshold, would be better to set a palette to show different classes with different colors. So make a new parenthesis here, and now the minimum value for class is number 1, the maximum value for the classes is number 5, and the palette helping us to show different classes with different colors. So 5 colors you can define here, one color for one class. So from white to red, white, yellow. Let me to go to next line to have more space for the writing. So orange, red, and brown. So 1, 2, 3, 4, 5. 5 number and 5 colors and 5 classes. So run the code again. In the right panel, we have urban heat island class. If you check it on, you will see that the urban heat island around the urban area uh, completely show the urban area as a hotspot in the analysis. Although there are also the other regions that's entitled as a strong or a strongest strongest thermal variances, or showing the very strong thermal variances, but this is happened sometimes in the images that we can ignore them by masking the extra region. The masking extra region is very important to avoid to have such kind of actually errors in our estimations. So what we can do for now, the best way in this step is use a land cover map to remove the extra pixels for the computations. So for example, here I'm gonna use MODIS land cover map. Here we have MODIS land cover type, yearly global with 500 meter, imported into the code as image collection number 2. Now I'm making a new variable for the land cover equals to, as I'm gonna to highlight the urban area, the variable name should be urban related to the application Earth engine.image, the collection number 2 or image collection number 2 here, image collection number 2 assigned to the urban variable, and then we need to call the land cover layer for 2020 because the urban heat island in this tutorial is related to 2020. Throw the dot filter date, start date is time start and end date is time end, just like that. So then we need to select one of the existing land cover land cover bands available here. Most of the time we are using LC type number 1 as a target land cover map in the most of applications. Throw the dot select function, select the target band, this is, and then throw the dot to bands. Now we are converting one image collection to a single image. So in this image, now I'm gonna select the urban area in a binary format. So first we need to know which values in the LC type number 1 showing the urban area as urban class. Go to the data description. In the bands there is a table or class table for LC type number 1 and other classifications available here, or other maps available here. Class number 13 showing the urban and built up surfaces and pixels. So now I'm gonna select the urban areas, throw the dot equal pixels including value 13 here, just like that. And now throw the map.add layer. I can show you the urban layer only highlighted the urban areas in the final map. So map.add layer, urban, clip it based on the ROI, leave the visualization empty. This is urban layer name and use the false at the end. Run the code, and here you can see that the urban area is highlighted. And now according to this binary image that's showing the urban area or residential area, we can mask the actually urban heat island classes that is already created. So now I'm making a new variable, for example urban heat island class number 2 equals to get the previous or existing urban heat island class and then through the update mask I can remove those of pixels correspond to the dark regions. Dot update mask according to the urban layer. Then using map.add-layer we can visualize the final estimations. Urban heat island class number 2, clip it based on the region of interest, and this is class number 2, and run the code again. Here, as you can see, urban heat island for class number 2 only showing the urban heat island or thermal variance over the Tehran city and also the surrounded region. As you can see, the biggest thermal variance is related to the, or strongest thermal variance related to the central region, and as far as we are going outside of the city, actually the intensity of the thermal variance reduced to the weak class. So that is the tutorial that helping us to get urban heat island thermal variance using MODIS and nighttime data that specifically you can be used for actually arid and semi-arid region. If you still has any question regarding this tutorial, you can reach me out through the YouTube channel, through my YouTube channel. And also, if you want to get export from the output that is created here, it's very simple. Just write export.image to drive. It is an applicable function helping you to get export from created image or created output with image structure and saving them into Google Drive. Some arguments should be considered in the image to drive. The first is the image, the target image you want to save, that is urban heat island class number 2, that is already masked according to the non-urban region, and then description related to the name of the output. For example, this is urban heat island for the arid and semi-arid region, and the scale of processing is important, should be 1000 meter because of a spatial resolution. The region of the interest should be ROI. The maximum pixels equals to 1E13, and also the CRS or coordinate system equals to for WGS84 this code should be used EPSG 4326. This is the code that we use for WGS coordinate system that globally can be used and without any problem. And so these are the main parameters, but the one thing that is remained, it is optional. You can set a folder or make a new folder to save the final result in. For example, I'm gonna make a folder as a test in the Google Drive to save the output in. So run the code again, this time in the console and task. Invalid JSON is a kind of error that sometimes happened, and it is not related to the programming technique or syntax error, just sometimes happen because of some net issues. You can run the code again, and now this time problem solved. In the right panel in the task, urban heat island arid is available, and now I can run the code and save the output. And also remember to clip the output based on the region of interest. That's very important thing. If you want to have the output clip based on the actually the border exactly, you need to use that clip in the image to drive again. So that's it. And if you had any problem regarding to the code link is available below the video description in my YouTube channel. You can check your codes with mine, and if a still problem exists, reach me out through the YouTube channel and put your comments, ask your question. I will try to check them and answer them as soon as possible. Thank you for your attention.